Okay, it's Berkeley time. Let's start. I see that there are questions in the chat. The instructors who are here with me, they'll try to answer them. I think the lecture slides were posted to Piazza. Yeah, the recordings will be released once we have them processed, because like when you record on Zoom, it usually takes time to there's like a pre-processing thing. Yeah. Okay, so for this week, we'll talk about content-based recommendation systems. By the way, can you all hear me? Okay. Yeah, for this week, we'll talk more about content-based recommendation systems and word embeddings, which are useful for content-based systems. So an outline for today, we'll recap the basic idea of content-based systems from week 1. Then we'll revisit binary representations and dot products and go through an improvement on the dot product, namely cosine similarity. And then we'll also look into sort of an improved version of binary representations, which is TF-IDF. And then we'll look at word embeddings and how they're trained. The two specific forms of word embeddings we'll look at are word2vec and glove. And then finally, we'll discuss some similarity measures for content-based systems, because usually in these content-based systems, you have the two main problems are, one is how to represent items, and the second is how to compare items. So similarity measures are the way to basically find items that are similar. Yeah, and finally, we'll talk about the limitations of these methods. So just a simple recap of content-based recommendation systems. These are, in a sense, the most simple form of system, where you basically just look at the items that a user has viewed in the past and try to recommend items that are similar to those. And there's like a implicit assumption that in the scenarios where you would use content-based recommendation systems, you assume that the actions that a user has taken in the past, you assume they're very informative of what they'll do in the future. Otherwise, it wouldn't make sense to recommend things that are similar. Yeah, so it works better in cases where most users have a long history of interactions. So like YouTube and then the social media in those applications, the user usually has a very well-established set of preferences, which can be inferred from what they viewed in the past. Yeah, and then one of the problems in these systems is building quantitative descriptions of items. So sometimes your item might be hard to quantify. Basically, like if your item is a certain user, like for Facebook, you would want to recommend users, right? And then there isn't an obvious way to simple to quantify a video as a set of numbers. So one of the problems in content-based recommendation systems is finding these quantified representations such that it becomes easier later for us to compare items, right? So the intuition of the representations we'll look at is basically they need to help us capture some form of similarity. And then revisiting our example last time, our representation for this example, we have a set of apps that we would want to recommend. So the binary representation will just have one entry for each category, and that entry will be marked 1 if a certain app belongs to the category, and it will be 0 if the app doesn't belong to the category. And then to infer user preferences, we'll just kind of take the average of all the apps that they downloaded in the past, and then take the dot product between that average vector and a new app to decide how similar this new app is to the apps that this user has used in the past. Yeah, it's very simple. It's a very simple system, but it sort of captures the basic ideas of why you want these vector representations and what you want from the similarity measure. And like here, the similarity measure is just using the dot product. Yeah, so just a recap again, a dot product is just taking the dot-wise product, taking the entry-wise product between two vectors. So from the last slide, if you want to take a dot product between the first two apps, you will just take the product between the value of the first app in the first entry with the value of the second app in the first entry, and then take the product in the second entry and just add them up. In this case, the dot product would be 0 because they don't have any common categories. And so in this case, the dot product basically just tells you how many categories two apps have in common, which kind of makes sense because the more they have in common, the more similar they are intuitively. But we will run into a problem where, say, an app is maybe very versatile, so it covers a lot of categories. Maybe it belongs to every single category there is. And in this case, the dot product will almost always select this as the best match for any app, just because it'll always have the most amount of common categories as other apps. And while our intuition that more common categories means a better match worked for previous examples, it doesn't necessarily work here because we're lacking the specificity in these categories, right? We would much rather prefer an app that has categories in common, where and doesn't have categories in common. So what I mean is, like, if all the items that the user has used in the past don't belong to this healthcare category, then we would rather recommend an app that doesn't belong to this category than an app that just spans every single category. And this is where we introduce this new similarity measure called cosine similarity. And the idea here is, instead of just looking at the dot product, and geometrically, the dot product is the area spanned by the two vectors, right? By that I mean, if you construct like, so we can interpret, first of all, we can interpret these vectors as sort of geometric objects, and we can think of them as arrows in space, where basically its position in each axis is just the value of the vector in that entry. So x1 here would just represent the first entry of the vector, and the next two is the second entry. So when we visualize these, they're arrows in space, and what the dot product corresponds to is if you take two vectors and you construct a parallelogram out of them. So imagine extending another copy of v1 out of v2 here, and then extending a copy of v2 out of v1 on the other side, and then they'll meet at the far end of the graph, and then it forms a parallelogram, right? So what the dot product measures is basically the area of this parallelogram. Now that, in some ways, that captures, actually, never mind. It's the length of one vector projected onto the other, multiplied by the magnitude of the other. What I was talking about earlier was cross product. Never mind. Yeah, so basically, it's some sort of alignment between the two vectors, but it also considers the actual length of both vectors. So if you just have a very long vector, it'll always have like a large dot product with other vectors, just because like its magnitude. Like even if it doesn't align very well with the other vector, it'll still give you a large dot product, which is what we saw with the app that just spans every single category. What we want instead is a similarity measure that just measures alignment and doesn't really care that much about the actual magnitude. So what we actually want is just this angle theta. And how we get that is using this formula. So the dot product of two vectors divided by their respective magnitudes actually gives you the cosine of this theta angle between the two vectors. And then because cosine is monotonic, we can just use this as we can just use this as a measure of how aligned they are. Yeah, and the advantage of this is basically it penalizes vectors that are long and it penalizes vectors that are unspecific in a sense that when they represent like an app, they're unspecific in the sense that they might span a lot of categories, but they don't specifically span the ones that you want. And so if we go back to this example, having extra categories that don't match the user preference will actually decrease your similarity score, because you can imagine that even though the vector is becoming longer, it's being sort of shifted in an unwanted direction. So your angle will still increase, even though your vector is longer. Yeah, and the angle between vectors isn't actually well defined in like a geometric sense for higher dimensions. Because like imagine 4 dimensions, what exactly is the angle you're looking at? But we can still extend this formula to higher dimensions, and it still captures alignment in the same way. Yeah, and now we move on to applying these things to processing text descriptions. So let's say your items are described by a paragraph of text, something like, so if you're recommending movies, maybe your movie is described by this passage, the adventure continues and blah, blah, blah. And you would want to convert this to a vector representation with that can be represented by a set of numbers. Yeah, and the other property that you want with this quantified representation is that you want similarity measures to work on this. So basically, text passages that mean similar things should have similar vector representations. Now, the most simple approach here is what's called a bag of words, where you have a vector and you basically assign a word to each entry. And the value at that entry would just be the count of how many of those words appear in your passage. So in this case, you have at as the first entry. And in this particular passage in the middle, at doesn't show up, so the value is 0 there. And then bat shows up twice, so the value is 2 there. And you can notice like bats and bat are both counted as bat, even though the first one has an S. So like some pre-processing will be involved to remove punctuation and also make words that basically mean the same thing into the same form, right? You wouldn't want this capitalization messing with your word counts, because basically your bag of words would be more meaningful if you're able to collapse words into larger classes, right? You just want your program to know that, okay, bats with a capital B and bat are basically the same object. We'll count them in the same category. Yeah, and the main problem here is basically, I mean, this is just a very basic way to represent text, right? You know that it's problematic because like a human looking at just this vector, and even if they know what each entry corresponds to, they can't, it's very hard for them to actually tell what this text originally was saying. So when you convert to bag of words, you lose a lot of semantic meaning about the sentence, because first of all, it doesn't capture any word order, and also words are considered equally important in bag of words, in the sense that like obviously if you have a word like elephant, it should be more important than like how many instances of the appears in your sentence, just because like the appears everywhere and it doesn't mean much when it appears more or less in a particular sentence. And that is what brings us to TF-IDF. The whole name is term frequency times inverse document frequency. So the intuition here is that rare words should be considered more important when they do appear in a document. By document, we just mean a particular passage, or when you're talking about items, the text for that item is considered one document. And here, what inverse document frequency means is, so we want to diminish the weight of terms that occur in a lot of documents, and then we want to reward terms that occur very rarely, raw count of a particular term in your passage. So here, the parameters in the function, t is just the what your term is, so a particular word in this case, and then d is the document, so the passage you're looking at. So what this means is basically you're just the term frequency is just the raw count of the term you're looking at over the actual length, over the length of the document. Like this, the thing on the denominator, it sums over the frequency of all terms. So basically, it just gives you the length of the document. Yeah. And then there are also some variations to term frequency, and they're all designed for like very specific properties. So one thing you can do is normalize by the maximum count of terms instead of the total count. So instead of putting the total count of words on the denominator here, you put the maximum frequency of any particular term. Or you can add a constant term for smoothing. The reason you would do this is because sometimes you don't want a small change in the frequency of the word to affect its TF-ID score too much. So, for example, if you double the frequency, sometimes it's not. Sometimes doubling the frequency shouldn't mean that that term is twice as important in your passage. It might be like 1.5 times more important, and that's why you add in this constant term and this and a coefficient to sort of diminish the direct effect of changing the frequency here. Yeah, and then the more interesting part of TF-IDF is the IDF part, inverse document frequency. So the formula here, once again, here T is the term we're looking at, and capital D is the set of all documents. So it would be all the items, like the passages from all the items that you have. This is more of a global parameter because you're not just looking at the passage for your one item. You need to look at all the documents to figure out how much your term is, how much your term should matter, right? And then, so inside the log here is n over, n is the total number of documents. N over, what this bottom term says is basically the number of documents which contain your term T. So what this is just the total number of documents over how many documents contain your term T. That's the, it's basically what you would call the inverse document frequency, but we also put a log in front of it. And the reason for this, there are several reasons for this. The main one is just that it's worked better empirically. There are also some information theoretic reasons for having a log there. And then intuitively, you can think about it as like the specificity of a term is sublinear compared to the inverse occurrence count. And what I mean by that is when a document, when a term becomes twice as frequent across the documents, once again, it should not be half as important. Maybe it should be like 1.5 times less important. But this log here just ensures that it doesn't decrease linearly as it would if you didn't have the log.
Andre, I think you froze sometime before term frequency. There were some like suggestion in the chat.
Oh,
just real brief.
Before term frequency. Is it this slide? Slide before this?
Yeah, I don't know. Let me see the response in the chat. But I think the slide before term frequency is yeah, TF IDF.
Okay.
I believe that one. Maybe like just briefly over.
Yeah, so to go over this briefly, TF-IDF is like an improvement over bag of words, where you start to diminish the weights of terms that occur in almost all documents. So what you're saying is, if your term, like a word like the or a word like is, they appear in almost every document, right? So that should tell you that them appearing in a particular document doesn't mean as much as a rare word appear in that document. So what TF-IDF does is basically take bag of words, but then add in these weights that tell you how specific a word is. And that's what you see here in this formula. So the term frequency is very similar to bag of words. In bag of words, you just have a raw count of the how many times a word appears, right? For term frequency is normalized, meaning that it adds up to 1 basically. And then IDF is the more interesting part, where you start to diminish the weights of frequent words basically. So going over the actual formula for inverse document frequency. So document frequency just means how many documents out of all the documents does your term appear in. So if it appears in half the documents, then the document frequency would be 0.5, right? So the IDF actually takes the inverse of that, because you want to diminish the weights of popular terms. So the inverse sort of creates that sort of relationship. And then the log in front is just to make sure that the actual weight is sublinear with respect to inverse occurrence. So what that means is it doesn't increase as fast as linear. It increases a bit slower than linear. Yeah. And then so you can apply TF-IDF with cosine similarity, because after all, TF-IDF is just another way to turn your text passages into a vector representation, right? And then cosine similarity is the thing that helps you measure the similarity between vectors. So you can have a system where you use TF-IDF to convert items to vectors, and then you use cosine similarity to make recommendation of similar items. So the more specific way of how you would do this is you will go over every item and you run TF-IDF on it to get a vector that represents it. And then let's say you want, and then this is like the preparation step. Then when you want to make recommendations, say the user might pick out a particular item, and then you want to recommend items similar to that one. What you would do is you'll take the item that the user that the user gave you. It might be something from their history, it might be something they searched up. You will TF-IDF, you'll get the TF-IDF vector of that item, and then you'll take the dot product between that vector and every item in your library that you have gotten the vector of. Right, and then you'll get a bunch of cosine similarity scores, and you'll just find the top scoring items and basically recommend those to the user, because those are considered the most similar under our system. Yeah, and here's a visualization of how cosine similarity works. So when the vectors are aligned very closely, meaning there's a small angle between them, the cosine will give you the cosine theta will be large. Actually, I made a mistake earlier. I said cosine was monotonic, but it is actually the opposite. It's cosine theta is larger when theta is smaller. And then it's cosine theta is smaller when theta is larger, and that's basically what's happening here. For orthogonal vectors, you'll get cosine equals 0. And then for opposite vectors, you'll get a negative cosine score, which is, I guess, considered even worse than being not aligned at all. Yeah, and so this is just like a basic comparison between bag of words and TF-IDF. Both of them consider frequency, but bag of words doesn't consider the specificity of a word. It considers all words equally important, while TF-IDF, it rewards rare terms. And then neither of them actually consider word order or semantics. They don't really read into the text as a human would, right? And this is where we start talking about word embeddings. And the reason I say learned word embeddings is because this is actually a more ML-based approach than it is the classical approach. So what a word embedding is, it's a learned representation for text where words that have the same meaning have a similar representation. And so the basic idea here is that we're going to find these vector representations using machine learning. But it's not immediately clear how you use ML to do this, because this can't be a supervised learning approach, right? Because in a supervised learning setting, you would have labeled data, which means you should have words that you know the correct vector, that you know the correct representation of. But so you can imagine producing that sort of data set with experts labeling it, but it's not clear what they should label, right? There's no consensus on which features define a word. So even if some linguists came up with vectors for a certain set of words, it might not apply well to all the applications. It's more useful if your model somehow knew to learn the embeddings that worked best for a particular system, right? You would have an objective at the end, like your objective might just be the recommendation accuracy. And then you want that objective to sort of guide what kind of word embeddings your system learns. And that's why I say these are sort of induced vector representations by training on auxiliary tasks. So the idea here is the training task itself is not a supervised task where you're trying to learn the word embeddings. Instead, the system learns the word embeddings by trying to learn some other task. Right, and then this visualization sort of shows you what we want from the word embeddings. So the newspaper and magazine are similar in meaning, so their vectors will point in a similar direction. And then biking has a very different meaning than those two, so it just points somewhere else. Of course, the actual word embeddings will be much higher than three-dimensional, because you can imagine there just isn't enough space in 3 dimensions for you to like arrange all the words this way. And okay, so we'll start with the embedding matrix. I'll say it's a matrix, but it's not actually that complicated. So what it does is basically it stacks the vector representations of words into a matrix. So if you have 10,000 words and you decide that, okay, each word will have a 300 dimension vector, then your matrix would just be a 10,000 by 300 matrix. Okay, but of course you don't start off knowing what the vector representation is. So you'll just randomly initialize to something, and what it actually ends up being is what we'll learn later. Okay, now these are like the weights in a neural network. Basically, you start by initializing them to something and just assume that your neural network will learn it by training on some task. Yeah, and the reason we stack them this way is because it allows us to retrieve the embedding for a particular word through matrix multiplication. So in this image on the bottom, the vector on the left is basically just a retrieval vector in the sense that like you put zeros everywhere except for the index of the word that you want to retrieve. And what happens when you multiply it by the matrix is that it just retrieves the correct it just retrieves just the embedding for the word you queried, basically. Like the matrix product is just that one row in the matrix, and that row represents the word at this index. Okay, word2vec is one approach to word embedding where given a word, you're trying to predict the distribution of context words. Now, what we mean here by given a word is that your model will know, like, so yeah, your training data set will consist of these pairs. Like, okay, you start with a text corpus of just text. It doesn't have to be labeled in any way. And what you're really interested in is just the distribution of words. And then from the text corpus, you'll generate these training samples, which are pairs, and the pairs will be generated in this way. So you'll find a center word. It's clear in the bottom 2 lines because in the first 2 you're like at the edge of the sentence. So you pick the center word, and here it's brown, and then you generate a pair for each of you generate a pair between brown and each of its neighbors. So brown and D is a pair, brown and quick is a pair, brown and fox is a pair, and so on. And then you move on to the next word and you do the same for fox. And the reason you create these pairs is that you want your model to be able to take in the word D and predict how likely it is for quick to show up in the proximity of your word D, right? Obviously, you're not asking the model to predict what the actual word is because that's just impossible. It also doesn't make sense. It also doesn't make sense as a task. Like you can look at brown, and there are a lot of possibilities of words that show up before and after brown. But there is a difference in how likely they are to appear. So some words are definitely more likely to appear before and after brown than other words. And even though your model doesn't predict what exactly shows up, it's able to, you are asking it to model the distribution of words that show up around it. So you want it to understand that, okay, fox is more likely to appear after brown than like dog. Obviously that might not be true in general. It depends on your text corpus. And if your text corpus is long enough, it should accurately represent the relationship between words. Yeah, and so how exactly do we do this modeling task? Well, remember that we did create an embedding matrix earlier, where we just said, okay, the row, the ith row is the word embedding for the ith word. And what we want to do is basically, like you start by trusting your embeddings to have the properties that you want them to, because like in the end, you're going to train them to have those properties, right? So what you want, the properties you want from these word embeddings is such that if you multiply the word embedding of word I with the embedding of word J, you'll get a similarity score between word I and word J, right? What you want this score to model is the probability that J shows up in the proximity of I, right? And that's what our training pairs were for. These training pairs should tell you how the actual likelihood of word J, just the word on the right, appearing in the proximity of word I. And then, so you have that distribution represented by the data. And now you want to learn from that data and create word embeddings such that their dot products actually give you these probabilities. Yeah, and in the actual implementation, it can be sped up much more than just computing these pairwise dot products, because like in a matrix, when you multiply matrices, you're also taking a bunch of dot products, right? So there's a way to align it so that in the matrix product, you're actually computing all the dot products that you want. So let's say you have the word ant, you have the word embedding for ant, and you want your model to predict the distribution of other words. So you want it, what you want your model to predict is, given that the center word is ant, predict the probability of say car being in the next 2 words, or the probability of another word like tree being in the next 2 words. What you'll do is you'll take the word embedding for ant and you'll multiply it by this whole word embedding matrix. And like if you look into this matrix multiplication, it's just taking the dot products between the word ant and every single embedding in the matrix, right? Because you basically take out this red vector and you take the dot product of it with this vector, and that gives you one entry in the resultant vector. Yeah, and so what you're multiplying is just the the transpose of the embedding matrix. So after multiplication, what you get is a vector that's 10,000 entries long. right? It's 10,000 entries long, and at the ith index is the similarity score between ant and the ith word. What is not shown here, so that vector isn't shown here, but that vector is immediately fed into this function called softmax. I think we talked about this last time in the machine learning lecture. But what the softmax does, it basically, one thing it does is it normalizes all the probabilities, so they all add up to 1, because like probabilities add up to 1, right? But you have no guarantee that your dot products actually add up to 1, so you need to normalize them. And doing the exponential is also a way to interpret the dot products as probabilities, because actually what you're asking the dot products to predict are the log probabilities, and there are some more mathematical reasons behind why you're predicting the log probabilities instead of the probabilities directly. But basically what softmax does is take the log probabilities, turn them into actual probabilities. So that's why you do the exponentiation, and then also normalize it. And all this, you can also think of it as a neural network, because remember, when you're doing feed forward in a neural network, you're also just multiplying matrices, right? The weights from one layer to the next can be represented as a matrix, and applying those weights is just multiplying by the matrix. So in this case, you would have basically one hidden layer, and your hidden layer, the vector, the weights from your input vector, which is this one hot vector denoting which word you're putting in. The weights from this one hot vector to the hidden layer is your word embedding matrix. And the reason is that you want the values at your hidden layers to be the word embedding of the word you put in. So just multiplying by the word embedding matrix will give you that. And then the weights from your hidden layer to the output layer is E transpose. And that's what we talked about here. So multiplying the word embeddings, multiplying a particular word embedding. So remember, when you feed this vector in and you compute all the weights between the input and the hidden layer, what you'll get at the hidden layer is each neuron will have the value of one entry in the word embedding of this word. So like if you feed an ant, the first neuron in the hidden layer will if you multiply by the word embedding matrix, the first neuron here would just be the entry of the will be the first entry of the word embedding for ant, and the second one will have the value of the second entry in the word embedding of ant, and so on. And so at this point, the hidden layer just encodes the word embedding for ant, and so multiplying by E transpose will get you the predicted probabilities of other words being in the proximity of ant. So that's why the weights here can be represented as E transpose. Can you still hear me? Okay, some people are telling me I'm being cut out. Yeah, and then the somewhat confusing thing here is that we don't actually start with a trained neural network, right? Because when we build neural networks, we assume these weight matrices are there. We just know that the weights aren't optimized. It's the same thing here. We just have this embedding matrix, but the embeddings aren't actually learned yet. So we construct this neural network and we want it to predict certain things. And then we train it to actually predict those certain things. And in the process, it'll tune all the weights, just like a normal neural network would. And what it's doing while tuning the weights is actually just tuning the embeddings, right? Because the embeddings are the weights. Now, there's one detail that is different from a normal feed-forward neural network that you might have seen in that last lecture. Here, like in a usual neural network, the matrix that takes you from the input vector to the hidden layer would be a different matrix than the one that takes you from the hidden layer to the output layer. But in this case, they're both the same matrix, except one is transpose. But the point there is that because they're the same matrix, when you calculate the gradients, you actually have to account for this dependency between the two matrices. But gradient descent still works, basically. You'll still get, you'll still be able to optimize it. Yeah, okay, so once again, you ask your neural network to take in a word and predict the probability of every other word being near your given word. And then your data for this task would be the pairs you collected from your text corpus. So each pair tells you, each pair should give you a gradient saying that, okay, this word, the second word is likely to appear near the first word. And then with the data, your network should learn this distribution. So now what that means is that, so let's assume that your network is already trained. It's able to predict the probabilities of other words being near a specific given word. What that means when you look back at this matrix multiplication is that the vector is that the dot product between the given word and every other word corresponds to the probability of them being close to each other, right? That is how we predicted these probabilities. So the fact that the fact that your network can predict these probabilities tells you that your embeddings have this property of co-occurring words being co-occurring words having large dot products. I think we're a bit short on time, so this is a very similar approach. It's also using word embeddings. It's also inducing word embeddings by predicting some sort of probability distribution over the text. But it's basically, it's very similar. So we'll skip this for this lecture. You can look into the slides if you want to. Yeah, basically the approach we looked at is predicting context words. Basically like context words, I mean like the words around a word. The approach we looked at looks at the center word and predicts words around it. And the other approach is just looks at the words around it and predicts the center word. They're very similar in nature. But the other approach, which is a bit different, is called GLOVE, global vectors for word representations. And the objective here is we don't have, we don't look at the proximity of words, but we learn word vectors such that their dot product equals the logarithm of the word's probability of co-occurrence in documents. So we want the embeddings, in this case, we want the embeddings to have dot products that corresponds to the likelihood of two words being in the same document. And that captures some sort of relatedness. Yeah, so here, this table is supposed to represent the sort of distribution we're trying to model. So, and on the left is the given word, right? You're given the word ice, and you want to predict the probability of several other words being in the same document as ice. So you have solid. This is the log. This is the probability, right? And then if you look closer, you'll realize that okay, ice has a higher probability of co-occurring with solid than it has with gas or with fashion, right? And that sort of makes sense because these two words are related. They're more likely to appear together. And steam is more likely to appear with gas as compared to solid. And neither of them are likely to co-occur with fashion because that's a completely unrelated word. And the approach for GLOVE is one of these approaches is matrix factorization. So once again, we're using the idea that you can take the pairwise dot products between a bunch of word embeddings by just multiplying the word embedding matrix. So once again, you'll have the embedding matrix, which is E, and taking the product E times E transpose will just give you a matrix of all the dot-wise, of all the pairwise dot products. So in the product E transpose, the ith row, the entry at the ith row and then the jth column would just be the dot product between the embeddings for the ith word and the jth word. And that's actually very convenient for this application because that is exactly that is exactly the thing you want to compute, right? You want all the pairwise dot products, and you want to use gradient descent to make sure that these pairwise dot products are similar to the pairwise co-occurrence rates. Right, like if you look back here, so the co-occurrence rate of solid and ice being high tells you that you want the entry in the E transpose matrix. You want the entry at row ice, the row of ice, and the column of solid. You want that entry to be large, whereas you want the entry at ice and fashion to be low. So you're just training E transpose to approximate the co-occurrence matrix, which you collect by just crawling the web for co-occurrence statistics. Now, there's some interesting structures just, that are discovered in these word embeddings. So remember, these are interesting because, like, remember, we only trained these word embeddings to put to put words that mean similar things closer to each other, or more precisely, we trained them to put words that co-occur together. We want to put those words closer to each other. And yeah, that's the theme for both of these approaches. Basically, we want the embeddings for co-occurring words to be closer together. So that's, but we also found more interesting structures in these word embeddings. You might have heard about these already. So what people found is that the vector differences also capture some sort of relative meaning between the words. So for example, the vector for queen subtracted by the vector for woman is very close to the vector of king subtracted by the word for man. So in this case, you can imagine, like, semantic wise, if you subtract out the gender for a queen and subtract out the gender for a king, like the residual meaning is very similar, and that's why these vectors are similar. All right. And these graphs also give other examples of this. So the relationship for between city to zip code is consistent across these pairs, and the relationship between a company and its CEO, its vector is also very similar. At least, like, it's pointing in a very similar direction. It's like aligned well between these pairs. Okay, and how you would use word embeddings for recommendation, that requires more NLP, which we'll go into later. But for now, we found a way to quantify words themselves, right? Although we aren't actually able to put an entire text into a vector yet, we're able to put words into vectors, and that's very useful because it allows us to use more neural methods like RNNs, LSTM, transformers. It allows us to use those to process word embeddings into sort of what we might call sentence embeddings. So we'll just have one vector represent a lot of text, and we'll talk more about that later. But for now, this is the point of having word embeddings. And actually, one more detail: when you begin to combine word embeddings into sentence embeddings, sometimes people actually just give up on word embeddings themselves. They'll just induce these word embeddings through the sentence embedding task. But it's also the case that when you don't have enough data, it might help to initialize your model with word embeddings trained from, say, Glove or Word2Vec, because those will give you sort of better gradients while you're training for the sentence embeddings. Yeah. Now, finally, we'll talk about some more similarity measures. We already went over dot product and cosine similarity, but there are actually a lot more. Yeah, one thing is Euclidean distance. It's like the first thing you do in geometry, I guess, but it's also meaningful in ML in measuring similarity. Euclidean distance is just the distance in R2 or R3 space, or however many dimensions you have. And then one example where this is useful is in Glove. So remember, Glove, we trained Glove to pair co-occurring words together with high dot products, but co-occurring doesn't necessarily mean that these words mean similar things, right? You can imagine I actually can't pronounce the name for these frogs, but you can imagine word 3 and word 4. They mean a similar thing. They both mean some form of frog, but actually it might be likely that they don't co-occur together that much, just because they might be mutually exclusive, right? Even though they're interchangeable, they might be mutually exclusive. So you won't get a high dot product between them. And this is where Euclidean distance comes in, because while dot product measures the alignment between two vectors, Euclidean distance gives you the actual distance between those two vectors, right? So dot product tells you how well the two vectors are aligned. Euclidean distance tells you how close their tips are. And in some intuitive sense, when your two vectors have tips that are very close together, they're just similar rather than most likely co-occurring, right? And so in this case, the authors that made GloVe use Euclidean distance to retrieve this different type of similarity, and they found these words to be closest under cosine under Euclidean distance. So like frog, frogs, toad, and then a bunch of other names for frogs. Yeah, this is just what I talked about last slide. Cosine similarity only looks for alignment, which in this case, alignment means co-occurrence. But Euclidean distance also looks for just absolute similarity. So these words need to be similar in both meaning and frequency. The other metric is Manhattan distance. So unlike Euclidean distance, which captures the fact that diagonals are shorter, Manhattan distance just tells you the distance you have to walk if you're only allowed to walk horizontal or vertical directions, basically. Yeah, so you're taking the sum of the absolute differences along each dimension, and that basically gives you the length of this green path or this red path. It's just like a rectangular path, I guess. Now, last we'll introduce two similarity measures for sets. So the first thing is dice coefficient. And what it does is it computes the ratio between the intersection computes the ratio between the size of the intersection between two sets and the sum of their respective sizes. So the intuition here is, say you have two sets that are very similar, so they have a lot of overlap, then they'll have a high intersection, right? If they're perfectly aligned, like if they're the same set, their intersection will have the exact same size as both of the sets themselves. So on the numerator, you'll just get 2x, or like just call it 2n, where n is the size of x. And on the bottom, you'll also get 2n. So the dice coefficient is 1 when your two sets are identical. And you can imagine the less they intersect, the smaller this dice coefficient would be. And you can also interpret this as a similarity measure between vectors, because you can think of vectors as binary representations of sets. So let's say you have, let's say in the original example, you might have two sets of 10 items and you want to compare how much they intersect. You can convert those two vectors by having two vectors that are both, let's say you have 15 items in total, and each set has 10 items. Then you can convert each set into a vector of length 15, which is binary, and it's one for entries where the set contains your item, and it's 0 for entries where your set doesn't contain the item. And in that case, the dot product between these two vectors is just the intersection. It just counts how many items they have in common, and the magnitude is just the actual size of the set. Yeah. And finally, Jacquard similarity is very similar to dice coefficient. Instead of intersection over the sum of sizes, it's intersection over union. And the same intuition applies. If they're perfectly aligned, the intersection will be equal to the union, right? Because both the intersection of a set in itself and the union of a set in itself are just the set itself. And if they're farther apart, it'll have, if they're farther apart, these two sets will have a smaller intersection, but they'll have a larger union, because when you overlap less, the union is larger. You're like wasting less. You're wasting less space in the overlapping parts. Yeah, and you can also interpret this as a measure on the vectors. Looks like we still have a bit of time. I will one second. Okay, we still have a bit of time, so I want to go over why we found these structures within the word embeddings, right? I mentioned these weren't exactly what the word embeddings were trained to do. They were only trained to capture co-occurrence, but somehow they also understand like relative meaning. The reason for this is because you can capture the difference in meaning between different words by the ratio of co-occurrence probabilities with other words. So what I mean by that is, let's say you're looking at the co-occurrence between ice and these 4 other words, and you're also looking at the co-occurrence between steam and these other words. So the difference in meaning between ice and steam, intuitively it can, it's not super intuitive, but you can sort of convince yourself that you can capture the difference in their meaning by how much more likely let's call this word W, right? You can capture the difference between the meaning in ice and steam by the ratio of how much more likely W is to occur with solid when you replace W, which is originally steam. When you replace it with ice, how much more likely is it to occur with solid, and how much more likely does it become to occur with gas, and all these other words, right? So in this case, the difference in meaning is sort of captured by, okay, when you replace steam with ice, you become 9 times more likely to find solid in the same document. You become much less likely to find gas in the same document. And it doesn't really change how likely you are to find water in the same document, because, well, these are both made of water. And it also doesn't really change how likely you are to find fashion in the same document, because fashion is unrelated, right? So when you exchange these words, you can tell how their meanings are different by looking at how the co-occurrence rate with other words change. So to give you a more detailed example, we know that ice to steam is like, at least the meaning is similar to, let's say, dry ice to carbon dioxide, right? These are 2 words, they're not a single word, but I didn't really think of any other 1-word example for this. But yeah, basically the first word is the solid state of the chemical, and then the second word is the gas state of the chemical. So we expect the difference in meaning to be similar. The difference in meaning is just the idea that we're replacing gas with solid. And so what would happen is, so if you added another row to the table and put this pK given dry ice over pK given carbon dioxide in the new row, you would expect the entries on that row to be similar to the entries for this ice and steam one, just because they have the same relative meaning, right? So replacing carbon dioxide with dry ice also should make it more likely for solid to appear, and also should make it less likely for gas to appear. And it shouldn't affect water or fashion. So you expect similar entries as the last row here. And when you take the log of these probabilities, Yeah, so basically the equation is that P K given ice over P K given steam is equal to, or at least like approximately, P K given dry ice over P K given carbon dioxide. And then when you take the log on both sides, you can expand out the division as a subtraction. So you get log P K given dry ice minus log P K given carbon dioxide is equal to, not equal to, but like close to log P K given ice minus log P K given steam. And remember that and this can be satisfied with embeddings that have this property, because remember, dot products are linear and our dot products predict the log probabilities. So if you have embeddings that satisfy V dry ice minus V carbon dioxide is close to V ice minus V steam, then no matter what K is, when you take the dot product with all four of them, because dot products are linear, you also get this sort of relationship between the co-occurrence probabilities. Yeah, and that's it for the lecture for today. We will release a quiz soon. Yeah, once again, like our quiz tests you on the last week, and then Amit.
I'm releasing the quiz right now on Piazza, and I'm gonna put it on the chat. I'm just like copying and paste it. The week is for every week, and yes, due tonight every week, and there will be it will be tested on week n-1, like the previous week that you guys have. So let me put it in the chat real quick. Wait a minute, just a second.
Someone asks, when is Manhattan distance used? So Manhattan distance is usually used when you're comparing two objects where these objects capture some sort of state that can be achieved through where you have state A and then state B. And there are some number of steps that you have to take to go from state A to state B. And in this case, you would use Manhattan distance as some sort of measure of the minimum number of steps, right? The reason why you're using Manhattan distance is because if you remember the image of the grid I showed earlier, basically you can think of like one vertical step or one horizontal step as like one possible step, right? In that case, the diagonal steps wouldn't be valid. So you have to measure the actual like number of segments you have to walk to get from one point to another. One example is like if you wanted to compare two positions on a chessboard or something, you might use Manhattan distance because like there are no diagonal moves. I mean, I not in chess, maybe in like Go, where there aren't exactly diagonal moves. Choosing between Euclidean distance and cosine similarity really depends on your task. In this case, like in the glove embeddings case, they find different things because the task itself was trained on cosine similarity instead of Euclidean distance. So Euclidean distance would find a different set of similar words. But like if you're asking about how to decide which one to train on, I think it's more common to use cosine similarity. I think one reason is because it's easier to compute. It's mostly just taking the dot product. But like there are also some cases where, like I remember there was, like Google has, Facebook or Google. So they had this model called a FaceNet, where they're mapping images of faces to points on a sphere, right? In that case, if your embedding is restricted to a point on a sphere, then Euclidean distance and cosine similarity, they basically measure the same thing. Because on a sphere, the smaller the angle between 2 points, then the smaller the Euclidean distance, right? So in that case, they're almost interchangeable. But I think they chose to use cosine similarity there. So word2vec trains word embeddings to predict. By predict, I mean it trains them so that the dot products correspond to the likelihood of word A being close to word B. That's word2vec. So word2vec is dot product models the probability of word A being in, it's a fixed constant, being in like 2 words, within 2 words of word B. And then okay, like word2vec is like a small window, the co-occurrence in a small window. Glove is co-occurrence across documents. So you don't care where in the document it is, you just care that, okay, word A and word B, we're in this document together. So that's one count of a co-occurrence.
Okay, and I think we're done for now, but like feel free to say if you have questions.